Up next, we have Dr. Bhamiti Sharma from the Center of Applied Energy Research, and her work is focusing on creating the synthetic graphics from the coal extracts. So let's hear from the Dr. Bhamiti.
Hey, good morning, everyone. Can you hear me fine? Okay, perfect. My name is Bhamiti Sharma, and I am a postdoc scholar with Center for Applied Energy Research. And today I'll be talking about how we can make graphite from coal. So first of all, we need to know why we want to use graphite for lithium-ion batteries. So lithium-ion batteries, as we know in today's day and age, it's everywhere. It's in portable electronics, it's in electric vehicles, it's in stationary, large-scale grid storage. And graphite is one of the major components of lithium-ion batteries, and we will see why. But before that, if we can figure out a way to convert coal to graphite, we can supply for the increasing demand of graphite for battery applications. Just to give you a number, 80% of the graphite is being imported from China, and there is going to be about 140% increase in the price of graphite by 2030. So it's very important that we have a local supply of graphite in the States, and it happens that Kentucky has a lot of coal, a lot of spare coal, which is dirt cheap, and if we can convert that to graphite, we have unlimited supply here in the States. So first, let's look at how lithium-ion battery operates and what is the role of graphite in a lithium-ion battery. So here is a small animation for you here. On the right, you can see that the right side electrodes is a positive electrode, the left side is a negative electrode, and the green ions are called lithium-ion. They are the major source of energy. They store energy and release energy when we use our phones or laptops. So as you can see right now, the lithium ions, which is green dots, are moving into the graphite structure. So graphite has these graphene layers which are stacked on top of each other, and lithium ion go and sit between the graphite layer. And that is the charge operation. During discharge, lithium ion go back to its host structure, and that's when we are using our phone after charging. So as long as there is lithium ion stored in the graphite, our phones are going to operate, our laptops are going to operate, and if not, then the battery is dead. So the main role of graphite in a lithium-ion battery is to store or release lithium ion during the battery operation. That's the key here. That is why we need graphite. So we have an excellent team at CAER. We have physicists, chemists, material scientists, and engineer from all different areas. We have been trying to solve this problem for 3 years now, where we can convert coal to graphite. So the team has perfected an approach called coal liquefaction, where we can take dirt cheap coal and produce a high value graphite for batteries. So just to give you an example, the coal structure is so complicated here that you see underneath the coal. And what we want to make is a completely different molecular structure for graphite. And we will see how. So there are many steps involved. There are 7 to 8 steps involved, and it have taken years for the team to develop this process. But I will divide that into 2 sections for your understanding. The first part is we take coal, which is very high in impurities because it's being mined, and we try to break down the big high weight molecular structure into smaller particles so that we can process that into graphite particles. And then we remove some of the ashes and impurities so that the impurities do not affect the battery performance. And the second step is to be able to have a structural arrangement of just the coal molecules that we have broken to graphite, that graphene layers. And then in order to do so, in order to facilitate that rearrangement, we need to bake these precursor materials to very, very high temperatures, or 2700 degrees Celsius, 3000 degrees Celsius. That is some of the facility that we don't have it here. We have to go to industry and they bake the powders for us to make that to a graphite. So team does a lot of characterization to make sure that this is a battery grade graphite. I will not go into the details, but we do follow the industry supplied specification for how a battery grade graphite should look like, what should be the particle size. So in this, I'll show 3 important parameters that we need to monitor. The first one is the microstructure of the graphite. How should it look like? What should be the surface area of it? So here you can see in this image that CaER graphite has smaller particle size as compared to the commercial graphite, and hence it has higher surface area. Those are the two properties right there. The particle size is also verified using the particle size distribution in a separate system. As you can see here, the commercial synthetic graphite has a higher particle size and broader distribution, and CaER is slightly smaller, but you will see here in a few minutes that our graphite is still good. Then the second important thing is the graphitization degree. So like I said, we bake our powders to 2700 degrees Celsius and 3000 degrees Celsius. So to make sure that it is converted to graphite, nice layers of graphene. So we have to get a number called graphitization degree that is taken by XRD, X-ray diffraction spectroscopy, where we take all these powders and perform the measurement, and we can see that the CaER graphite is only 80% graphitized to 2700 degrees Celsius, but we can use the higher temperatures to make better high value pure graphite. Now here is where my work comes in. The team does a lot of work there, but I test the battery. I test the graphite in the batteries. So the very first step is we take graphite, the team just produced, and then we mix that in a solvent so we can make an electrode out of it. So we make slurry, we coat the slurry onto a copper foil so that it's a physical coated electrode. And then, because we have solvent in it, we need to dry that in oven at 70 degrees Celsius overnight. Once that solvent dries up, it kind of leaves the gap behind. So we got to make sure that we close the gaps by compressing the electrode between two rollers. And that's what is called calendaring process. You see these rolled graphite in the third image from the last. And once that graphite electrode is ready, we punch it into desired shape and sizes so that we can put into the batteries. The battery here is called coin cell. So these are the small cells that we use in our car keys or I think small electronic equipments. So once the graphite is in the coin cell, the next step is to be able to test it and see how good it is as compared to the commercial graphite. So here you see two charts, and I'll try to do my best to explain that. First thing, we got to know what is capacity. So capacity is a measure of charge, meaning how many lithium ions can be stored in the graphite structure between the graphite layers that I showed in the beginning. If we can store more lithium ions, then we have higher capacity. If we store lesser, then we have lower capacity, and all that depend on the temperature, graphitization temperature. So you will see here that the red chart on the red line on the left chart here is a graphite that is heated to 2700 degrees Celsius. The green, that is 3000, and blue one is a commercial synthetic graphite, and the x-axis shows the capacity number. So you can clearly see that 2700 degrees Celsius, the red plot, is not as good. But if we use the temperature knob and increase the temperature to 3000 degrees Celsius, we can increase the graphite capacity. And on the right, I'm showing the cycle life, which means how many times can you cycle your battery, how many times can you charge and discharge before your battery dies. So in this case, I cycle the cells for 50 cycles, and you can clearly see that the green line, which is CaER heat-treated graphite to 3000 degrees Celsius, is as good as the commercial graphite. So the lesson here is we have, at CaER, we were able to make graphite from dirt cheap coal, and we have shown that we can test in lithium-ion batteries and it performs as well as commercial graphite that's available in the market. And we can use the graphitization temperature as a knob to change the capacity number, so we can still make this graphite better, and the team is doing that right now. I would like to acknowledge all the team members. It has been more than 3 years that we have all been working. The team has been working towards it. I joined a year back. And the big thing is that was not even a real battery. That was just a lab scale research. We still have a long way to go. We are going to make these batteries like test in a commercial testing in a coin cell and pouch cell format, and say how good the CAR graphite is. With that, I'd like to thank you all. Thank you, Joseph, for giving me the opportunity to present here. Thank you, everyone.